All right, hello, Discrete Math. Making a video alone by myself in a room on Tuesday evening. Snow day tomorrow. Woo! We can't fall any further behind. This will be our third missed block of period 8. That can't happen. So we're recording a video, we're watching a video, let's go! All right, well, first of all, a recap from last class. One thing that happened last class, at the very end of class, was this thing called the Euclidean Algorithm. And the Euclidean Algorithm, not to be confused with the Euclidean division algorithm, is an algorithm for finding the GCD of two numbers. And my explanation and lesson for this was like not perfect, but I tried to make some clarifying remarks on Canvas, and I think I did a pretty good job. Basically, what we did is we presented an algorithm which, well, it's given two numbers A and B, produces this new number E, and we showed that this algorithm terminates. We then showed that this number E can be represented as a linear combination, so a sum of products of constants times the numbers A and B, where S and T are integers. We then showed that E is a common divisor, that E divides A and that E divides B. And then we showed that if C divides A and C divides B, then that C divides E. In other words, what we've showed is that in fact the GCD of A and B is E. And this happened in sort of several steps. Obviously I'm not going to go through all the details again. And then the sort of grand conclusion is that the GCD of two numbers, A and B, can be written in the form SA plus TB, which is like not an obvious fact at all. Okay, so the next thing I want to talk about is also something that came up in last class, and I think I got all ready to prove it and then just like stopped because I realized, oh man, it's better if we have this first. So here we go. It's called the prime divisibility property, and it is again another one of these very, very low-level facts about numbers. Okay, what does it say? Or we talked about it already last class. Now we're just going to prove it, or I'm going to prove it. So it's let P be a prime number, and the theorem says that if P divides a product of numbers, so A1, A2, A3, to AN, then P has to divide one of them. Then P divides AI for some I, where I is one of these numbers on the right. And the way to kind of think about this is that a prime number like, I don't know, 7 or whatever, if it divides some product of numbers like 14 and 10, then it has to go into one of those numbers. Either 14 or 10, in this case it's 14. It's not possible for 7 to be partly in 14 and partly in 10. Whereas with 4, it certainly is possible for 4 to divide 14 times 10, 4 not being prime, but not to divide either of those two. So this is kind of a fact about prime numbers. Okay, so if this is true, then 7 must divide 14, or 7 must divide 10. In fact, it's that 7 divides 14. Whereas with 4, not a prime number, you can have 4 not dividing 14, and for not dividing. I guess maybe the best way to put this is to just state the theorem and say that it's false, right? So that 4 divides 14 or 4 divides 10, this is false, and this is true. So it's true when the divisor is a prime, and it's false in general when the divisor is not a prime. Let's see, we're still in frame. Looking great. Let's go. As I think we already even began the proof even. So we split up into a certain number of cases. So case n equals 1. Well, if n equals 1, this is pretty silly, because if n equals 1, then we just have p dividing some number, a single number, a1, then sort of trivially, if p divides a product of numbers, it divides one of them. Well, if p is only dividing one number, then p certainly divides that number. So, duh. Okay, so the interesting case is case n equals 2, and maybe it's actually nice to, well, let's just go in order, I guess. Okay, case n equals 2. What do we have to show? We have to show that if p divides the product of two numbers, p being a prime, then p has to divide a1 or p has to divide a2. All right, and I can't think of any other really possible way to do this except to do it by contradiction. And so that's what we'll do right now. We will assume, well, maybe just be a little bit more clear about this. So if that's the conditional that I need to prove, that's the theorem. So let p divide a1, a2. And in order to show that p must divide a or p must divide a2, suppose not. So suppose not. Well, the negation of p dividing a1 or a2 is by De Morgan law that, in fact, p doesn't divide a1 and p doesn't divide a2. And somehow I'm going to show that this is possible. All right, well, yeah. So, first of all, p is prime, right? So since p is prime, the only divisors of p, are p and 1. That's just the definition of prime. Well, if the only divisors of p are p and 1, and so now since p doesn't divide a1, then p is not a factor of a1, and the only factors of p are p and 1, and so that means that p and a1 have no factors in common. The GCD of a1 and p is 1. Again, the only possibility would be, I guess, p itself, since p is the only other factor of p, but p doesn't divide a1, so p is not a factor of a1, so p can't be a common factor. All right, and now it's totally non-obvious that this is like a good idea, but we now reach for this very low-level fact about the GCD of two numbers, that the GCD of two numbers can be expressed as a linear combination of them. And so, what we say is, so there are integers s and t such that the number 1, the GCD of a1 and p, can be represented as s times a1 plus t times p. Okay, and now we see that this is kind of impossible. Because by multiplying through both sides of this equation by a2, then we get that a2 is s A1, A2 plus T, P, A2. Okay, and well, something went wrong. A1, S, oh no, nothing went wrong. S, A1, I just have this a little backwards on my paper, but that's fine. Okay, so, great. Why is this a problem? Well, okay, you can kind of see what's going on here already, I hope. Yeah, oh, here it is. What the hell is this? Since P divides P, one second. Since P divides, oh, I see. Yeah, so, well, here it is, right? P divides A1, A2. Hold on. Since P divides A1, A2, then there's like a P in here. But now, there's also a P in here. So this gives us that P divides A2. Alright, writing this out, since P, and I'm going to run out of space, since P divides A1, A2, this is by assumption, then P must divide S, A1, A2. But if P is a factor of S, A1, A2, and P is also a factor of T, P, A2, then P must be a factor. Let's see if I can just squeeze this in. Since P divides A1, A2, then P divides S, A1, A2. Also, P clearly divides P, T, A2. So by the theorem that says that if P divides one number and P divides another, then P must divide the sum of those two, we conclude that P must divide S, A1, A2 plus T, P, A2. But that just is A2. So this says that P divides A2. But that is a contradiction with my assumption that P doesn't divide A2. Alright, what is really going on here? It's hard to do in a room with no people for inspiration. Each step of this proof is totally clear. What is sort of like really going on here, I guess? Yeah. What it sort of is saying, I guess, if you kind of sort of feel it, is that if P and A1 really have no factors in common, and that their GCD is 1, then well, I don't know if I have a deep analysis. I will think about this. I was just going to kind of recite each of those sort of lines of the proof over again. I guess it's this. Yeah, I think I'll stop there. All right. Wait, actually, we're not even done because this is case n equals 2. But I want. Let's see if my camera will get to the end of that line. It sure will. What I actually want is the full theorem, and it sounds like I'm only on case 2. Okay, but really we've done all the hard work already, because case n is greater than 2 is quite simple. So if we say if, so what is the case n equals 2? Well, now we say if P divides A1, A2, to AN, what do I need to show? Well, then the conclusion is that P divides A1 or P divides A2 or ... P divides AN. that's what we have to prove now. Okay, but that's actually simple if we have the n equals 2 case, because we just kind of like repeat this, right? So basically the gist is, so suppose P does divide A1, A2 to AN. Well, what we may do now is just express this as like A1 times A2, A3 to AN. In other words, multiplication is like a binary operation anyway, so there's no really such thing as a product of a whole bunch of numbers. Any product of a whole bunch of numbers can just be thought of as the product of one number times the rest of them. And now we will like apply case n equals 2 to these two numbers. And so now we say by case 2, we know that if P divides two numbers, then P must divide one of them. So P divides A1 or P divides A2, A3 to AN. Okay, well, if P divides A1, then we're done. We've shown that P divides one of them. If P doesn't divide A1, then just repeat. Just repeat this process. Repeat this process. And now it must divide one of these. Okay, so eventually we get that again. By case 2 again, that P divides A2 or P divides A3, A4 to AN. All right, and basically this process must terminate. So eventually, because each time we're pulling only n of these factors, we're pulling off each one at a time. So eventually, this process must terminate, and at latest must terminate at the latest with P dividing like the last two, so A minus 1 AN. All right, so that's pretty good. All right, there it is, prime divisibility property in all of its glory, and we'll use this a couple times. You already used this on your homework. All right, let's talk about something else. Let's talk about mathematical induction. Woo! All right, well, let's talk about what mathematical induction is, what it isn't. No, let's talk about what it is. Well, fortunately, virtually everyone in this class has already has a lot of experience with mathematical induction. Depending on how seriously I took this topic the year that I taught you, and some of you didn't learn the topic from me, I believe. All right. So what is mathematical induction? Well, it's the theorem which says that if all, it says the integers, or rather the natural numbers, have this certain property, whether you start at 0 or 1 sort of doesn't matter, that if you can show that 0 has some property P, and if you can show for any number whatsoever that whenever this property is true of a number, it's also true of the next number. If you can show all that, so now I'll put giant parentheses around this, then if it's true of 0, and whenever it's true of a number, it's true of the next number, then in fact it must be true for all numbers. And that this is actually true for all possible properties. So those of you who took logic, okay, we talked about this. We're sort of quantifying over all possible properties that a number could have, or all possible sets or something like that. what this says is, if 0 is one of the numbers that has this property, and if whenever a number has a property, the next number has the property, then all numbers must have this property. And it makes total sense. The way most teachers teach this is to say, okay, come on, this has just got to be true. Because if 0 has the property, and whenever a number has the property, the next number does also, then 1 must have it. And if whenever 1, and okay, so 1 has the property too. Well, if whenever a number has the property, the next number has it, then since 1 has it, 2 must have it. And similarly, 3 must have it, etc., etc. And you can show up to any finite number that all, without using the principle of mathematical induction, you can show up to any finite number that all the numbers must have that property by sort of proving this conditional in general and repeating it over and over again. But the sort of bold thing is to be able to state that all numbers have that property. And there are an infinite number of natural numbers, so to conclude that all numbers have that property, I cannot repeat this process a finite number of times. That will never get me to like infinity. And so the proof, the mathematical induction really is like a contentful statement, which we really do actually need to get to this conclusion that we want. All right, how does this work? I'll do like an easy example of mathematical induction to get yourself back into this if you haven't done this in 1 year, 2 years, or 3 years, or who knows, maybe never. So we'll take a theorem. Here's the theorem. The theorem is the sum of the cubes. So the sum from, how do we do this? I don't know, k equals 1 to n of k cubed. Everyone knows sigma notation, so I think that's fine. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, all the way up to n cubed. There's a formula for this. It's n squared, n plus 1 squared over 4. And, good. Yeah. Never mind how we discovered that. Maybe we did it by pattern recognition. Maybe we had some geometric argument. So never mind understanding it or whatever. Let's just go to verifying that this is true for all possible numbers. Well, this is where we're going to use the principle of mathematical induction. And it is helpful to nickname these. So I'm going to call this entire left-hand side A sub n, and this entire right-hand side B sub n. And so what I want to actually show is that for every possible number, the property that that number has is the property of this formula being true of that number. In other words, n is the sort of the number of cubes that you are actually adding, and showing that this formula works, or showing that this formula is true, is really a way of saying that this formula is true for all, not just sometimes, but for any possible n. Okay, how can we show that it's true? Well, mathematical induction gives us a guide. We first verify that it is true for one number, so the base case. So does the number, well, I think 1 is the place to start here. So we start with n equals 1. Does this property hold for n equals 1? Well, yes, because a1 is, by the use of the sigma notation, the sum from 1 equals, well, you stop at 1. And so it's just 1 cubed. And b1 is, well, it's like 1 squared over 1 plus 1 squared over 4. And that is, these two are equal. Okay, and so this property, the property of this formula being true, is true of the number n equals 1. All right, and now we make an inductive hypothesis. And our inductive hypothesis is that this formula is true. So we say, suppose that it's true for some number k. So suppose that a sub k equals b sub k. And then what we must show to complete the inductive step is that a sub k plus 1 equals b sub k plus 1. Okay, and all right, I picked an example that I thought was kind of easy and something even that we may have done this exact problem before. So I've made this assumption, and now I have this particular thing to show. Okay, well, what do we do? Well, I need to show a sub k plus 1 equals b sub k plus 1. So, what is a sub k plus 1? It is k was a terrible choice. Let's see. If I want to hold on to this, then I should just change this index to I. Yeah, there we go. Okay, so what is a sub k plus 1? A sub k plus 1 is the sum from I equals 1 to, well now I stop at k plus 1 of I cubed. In other words, this is just 1 cubed plus 2 cubed plus 3 cubed plus all the way up to k plus 1 cubed. Okay, that's, oh, and maybe I'll even throw in the plus k cubed plus. And this shows that, in fact, this is just the sum from I equals 1 to k of I cubed, plus just the final number being cubed, k plus 1 cubed. In other words, a sub k plus 1 is just a sub k, the sum of the first, the cubes up to k, plus the k plus first cube, which is kind of obviously true. Well, now I invoke my inductive hypothesis. I have assumed that a sub k equals b sub k, and since that's, therefore I'm allowed to just use that assumption. So a sub k equals b sub k. This is my inductive hypothesis at work right here. And this is k plus 1 cubed. Well, b sub k plus 1 is by definition k squared k plus 1 squared over 4. And I'm adding to it this k plus 1 cubed. Okay, so let's write this as like 4k plus 1 cubed over 4. And now we just have a little bit of algebra to do. In particular, I shall factor out k plus 1 squared over 4. And if I do that, I'm left with k squared plus 4k plus 1. And now we're just kind of done because this is k plus 1 squared, but this is k squared plus 4k plus 4, which is just k plus 2 squared over 4. And then this is, by definition, b sub k plus 1. Okay, so what happened, and there's this magic moment when everything always just works out. What really happened is, and I forced my students to write this sort of concluding statement down here. What happens is we verified by like direct computation that this formula is true for n equals 1. And we then assumed an arbitrary k, and we showed that on the assumption that the formula is true for b sub k, that it is true for k plus 1. This is my summary of what has happened in this proof so far. I assumed that the formula worked for k, and from that assumption showed that it worked for k plus 1. And so the property of the formula working has been inherited. And now we say, so by the principle of mathematical induction, in fact, for all n, this formula is true, that a sub n equals b sub n for all n. Okay, let's see if that's visible. Oh yeah, looking good. All right, well, what I would now like to do is something I certainly never did in pre-calc C, where we just took this as being something that was obviously true, and we didn't do it in logic either, because in logic we took this as an axiom. But in this class, we've taken a different thing as an axiom. Our axiom is, our sort of most basic axiom about the natural numbers is the WOP. And in fact, you can prove that this thing, which our book calls mathematical induction, is just a consequence of the WOP. Okay, so theorem. Our theorem is that the well-ordering principle implies this thing I just proved, mathematical induction. Okay, let's go. Let's prove it. All right. Well, what is even the WAP? The WAP is, okay, so let's list these. The WAP is the statement that every non-empty subset of the natural numbers has a least element. And of course, mathematical induction, I'll just repeat it here, says that for any possible property whatsoever, if you can prove that 0 has that property, and you can prove that whenever if a number has a property, that the next number has that property, that for any number that condition holds, then, here comes another parentheses in here, then for all n, all the numbers have that property. Okay, let's do the proof. And this is one of those things where if you took logic, this is going to be way easier for you, almost like essential. But anyway, we'll go through it. It'll make sense. Good. Woo! So, assume the WAP. Assume the well-ordering principle. You could argue that we just have assumed it as an axiom in this class, but I'm trying to show that this in fact implies this. And vice versa also. We will later show that from mathematical induction you can prove the WAP. So if we're going to assume the WAP, and way down here we are going to just have mathematical induction. So the very property of mathematical induction is itself being proved here. Okay, how? Well, mathematical induction says for any possible property, and then it says like blah blah blah. Okay, so if we're doing this really nicely, we should say take arbitrary property P. Okay, so given any property whatsoever, I'm going to now conclude what I need to conclude about that property, which is that if 0 has the property and whenever a number has that property, so does the next one, Jean, then all numbers have that property. Okay, how am I going to do this? Well, the statement that I'm trying to prove is itself a conditional. And since the statement I'm trying to prove is a conditional, the way to do it is to assume the antecedent and derive the consequence. And so I shall assume the very thing I'm trying to prove, that